Hello everyone! Thank you for joining to watch fourth and the last part of the video What Mobile Networks. In the previous three parts we discussed historical aspects, which were prerequisites for mobile networks appearance, as well as evolution of radio resources over the time in mobile networks, where radio is our bottleneck, which affects on overall throughput of sending data. And in the very previous part we dived a little bit into content of the mobile network to see what is inside. And the very last topic for this video will be about some evolutionary improvement trends which happened inside mobile networks on the way to 5G. We already discussed radio resources evolution. Now it's about evolution happened inside the network. It's not about node names change from generation to generation. It's about shifts of paradigms, which simplify mobile network integration and quick adjusting to high resource demand. When I started working with first-generation mobile networks, there were different types of transport protocols to connect neighbor nodes to each other. One of the reasons for that, it was related to circuit switch resource allocation. Similar to TDMA technology on radio interface, copper wires were logically separated by TDMA into several time slots, for example 32 in Europe and 24 in US. Each time slot is possible to reserve for voice call to one subscriber. Later, packet data appeared in mobile networks, and it was necessary to squeeze packet data transmission through the same time slots which were used for voice calls. There was a need to multiplex several time slots for one subscriber when possible to increase data throughput. Some parts of transport network may use ATM packet transmission, which is totally different way if compared to widely used IP connectivity. IP traffic was also used between some parts of the network. When you have different connection types with different ways of configuring, it makes nodes configuration more complicated. Important: each different way of transport protocol requires separate unique configuration approach. What amazing is happened over the time? It was process of transport protocol uniformity. Even nodes responsible for circuit switch calls, they at certain point started being connected by IP protocol. Then even voice services started moving to packet data communication. And what we have now? I cannot imagine any interface in modern mobile network which is not considered IP protocol as transport protocol underneath between any two nodes. It is so very convenient to have similar way to handle the same transport network protocol throughout the whole network. Imagine that you own a company which can build paved road surfaces several different ways. It might be cobblestone, granite sets, concrete, asphalt, or maybe any other type. Not focusing on price and convenience for cars aspect. Each approach requires totally different technology to build a road. You need to differently deliver materials. You need to differently train your teams per each type of road. You need to apply different procedures when building. That requires a lot of time to establish all business processes. It would be much easier to take care of just one type of the paved road to be built by your company, for example concrete roads. Business processes unification and simplifying are the keys to optimization and overall success. So first improvement within mobile network is transport protocol unification. All connections between nodes are IP based. Second thing, part of mentioned improvement is unification of all services to be IP based, including so-called voice over IP. That means there has been a huge shift for controlling, establishing and ending voice calls as well as transmitting voice itself by means of IP-based transport. Yes, old-style circuit switch technology used for voice services moved to have packet data network underneath. We can compare with historically separated reserved bike lanes, which was switched to different way of use, sharing paved roads between cars and bikes. Third interesting item is semi or even fully automatic mobile network parts configuration. When I started working with mobile networks long time back, I made a lot of integration activities between each two neighbor nodes. Each node needs to be configured to communicate with its peer, and it was done manually. Maybe you configured two computers to talk to each other by assigning proper IP addresses within the same subnetwork and proper routing rules. That is a simple example of IP address and IP routing configuration to be done before computers can start communicate to each other. Or analogically, to speak on the same language, two people need to learn language basics, naturally from childhood or studying somehow. We all kind of pre-configured to use language before communication starts. Mobile networks were improved over the time. Probably you've heard about self-organized networks, SON. One of the examples is dynamic IP routing. Let me explain it simplified. When you have two computers within the same IP subnetwork, there are certain mechanisms implemented to automatically exchange IP traffic between all nodes within this subnetwork. For simplicity, let's say that nodes within the same subnetwork have common IP subnet identifier, without digging now into details. When you have several subnetworks, there are routers between each two subnets to send packets between them, like bridges, gates between two islands. These routers to have one interface on each of two subnetworks, in our example. And you remember that within subnetworks, routing is in place. So from this interface on the router, packets can reach interface of any computer in the same subnet. But to route packets between two nodes integrated in different and especially non-adjacent subnetworks, there is a need for certain IP routing rules to be in place. For example, what needs to be configured and on which nodes to route packets from this computer in the first subnet to this computer in the third subnet. First computer needs to know which interface, if exists, in its own subnet can act as a gatekeeper on the way to the destination computer, which is router's interface. Like if you need to find route from this house on the island to this house in this island, first you need to know how to reach this bridge in your own island. First computer should have record. To reach this subnet, I need to send packets to this router's interface. Our example is simplified, but routers usually have more than two interfaces and two subnets they are connected to. So routers internally also need to have routing records which subnet to send packet on the way to final destination. Imagine for a second strange analogical example of a bridge connecting more than two islands. The right way to final destination can be found only with traffic signs explicitly mentioning directions to all islands. Traffic signs on each bridge can be compared to routing tables on IP routers. Let's remove third subnet here. Our routing table on this router will be simple, one record per each direction. But not so obvious. We don't send traffic towards node within this second subnet just based on assumption. A routing table of this router needs to have explicitly mentioned interface of the next middleman on the way, which is particular IP address of second router's interface. And this IP address is naturally reachable within this second subnet. So packets will go from this router to the next one. Next router also has its own routing table. For subnet of own interface, there is no need to explicitly mention next middleman though. It's enough to know which interface to send packet further. And within the last subnet, packets from router will be eventually delivered to the destination computer. Routing records on IP nodes, computers and routers, sometimes named IP routing tables, can be configured manually on each node. Such manually configured routing table entries are named static routes. If you add fourth island in your paved roads network, we need to update manually routing tables on lots of nodes which plan to be involved in traffic exchange. That's kind of a huge work to be done, isn't it? So dynamic routing was introduced with the main idea. Once you add new network segments, certain automatic dynamic routing information will be spread over participating parts of the network. From router to router, routing tables will be updated with new dynamic routes. Some protocols like OSPF, BGP and others can do that automatically. An analogical example may be futuristically imagined as automatic emails sent to everyone with notification that new bridge is opened and island number 4 is reachable by cars now from other parts of roads network. And all traffic signs on bridges are also electronically automatically updated with newly added information. That was example of SON networks. Such dynamic routing works not only in mobile networks, but utilized by them as well. Another SON example is mobile network specific one. and it will be about implementing automatic neighbor relations (ANR) mechanism. Imagine that 4G mobile network has two base stations named eNodeBs. There is a special interface named X2 between them for certain mobility scenario named X2 handover. In short, handovers are to quickly change radio resource, jump from one base station to another, and seamlessly continue to provide user service, voice call or packet data receiving, etc. When UE moves from one eNodeB to another, there might be a need for information exchange on X2 interface during each handover procedure. And you can guess both eNodeBs should have such X2 interface pre-configured to know which eNodeB to send traffic during handover. There were a bunch of parameters to be in place, and X2 interface configuration is not a 1-minute activity. And a network may have 1,000 pairs of eNodeBs, by the way. I manually configured lots of times such interfaces on eNodeBs in a testing lab. It's a time-consuming process. And one day, ANR mechanism was implemented. All that was needed is to just enable switch on ANR feature on both eNodeBs and on MME they both are directly connected to. Both eNodeBs have all required information to configure X2 interface between each other. All that is needed is a trigger for information exchange. That happens when UE moves from one eNodeB to another at a time of service, for example voice call. That triggers handover with several steps, not through short distance X2 interface, because it's not yet built. But centralized core network node MME is involved, which residing actually far away from eNodeBs. Before the very first such handover, eNodeBs didn't know they are neighbor eNodeBs. And after such handover, eNodeBs realized that they may immediately initiate additional steps for automatic information exchange through directly connected MME. During procedure, both eNodeBs send each other their IP addresses for future X2 interface along with all relevant radio resources parameters needed for both eNodeBs to automatically create X2 interface so eNodeBs can be connected later. Actually, it should be same amount of parameters which previously were configured manually before ANR was introduced. Operator may have thousands of eNodeBs. Their configuration, including X2 relevant, can be changed from time to time. Imagine how much time can be saved on the whole mobile network scale by having X2 interfaces configured automatically, and by the way, error-free, which is not always the case with manual configuration. ANR is another example of automatic configuration. Even other interfaces between nodes, they started being semi-self-configured. In earlier mobile network generations, to make interface up and running, you need to take care of lots of protocols in so-called protocol stack during configuration. It was a multi-layer mini project to configure several protocols or one after another on a node. One low-level protocol on interface on both sides. Network will start messages exchange on that protocol, and you need to ensure protocol is up and running. Then to move on the next protocol on the top of just configured, and so on, till all bunch of protocols, each with their parameters, come alive. It's like handling Matryoshka doll, peeling layer after layer. In modern IP-based networks, for example, to connect eNodeB to MME, it takes just a couple of parameters to be ready on both sides. And then you just enable eNodeB, tell that it's time to start. It sends just one message with couple of parameters and receives one answer from MME back. If answer is successful, interface between eNodeB and MME is up and running. Easy like a switching on lamp in your dining room. That was about simple, almost one-click modern mobile network nodes connecting to each other. Semi-automatic network configuration example. That's it for self-organized networks principle examples in mobile networks. Another improvement in mobile networks is control and user plane nodes separation. What does it mean, control, in this context, or user? Remember our example of node chain selection and preparing session, our pipe, for further sending traffic. That was an example of control plane messages. They control establishing, modifying, deleting resources throughout the network. And once resources are ready, they can be used by user plane traffic, voice or packet data sending to from mobile phone. You can compare control plane messages with some live examples. Like few steps of action to start your video conversation via some messenger. You need to open Messenger application. You need to find user you want to call. You need to ensure remote user is online. And finally click call button. On the other user side, if he was online, he receives call and notified by some sound, needs to find and click answer button. All these small steps are kind of a control conversation to be started. And actual audio-video sending both ways is in turn about user plane messages exchanged. You can control your user data during a call, for example, switch video or audio on and off, or at the very end, hang up. 15 years back, it would be very hard to imagine what a huge data throughput could be achieved via mobile networks. Nowadays, you can watch video of a very good quality through mobile phone or tablet. It implies that just few small control plane messages can be followed by enormous user plane load. And now imagine millions of users on the whole mobile operator scale. Central processor and networking power of mobile network nodes to handle controlling messages and user plane traffic therefore is very different. To strengthen, user plane traffic growth is very significant year after year. What happened with mobile networks in regards to that? Nodes in first mobile networks were capable to handle both types of traffic, control and user planes. But soon they started separating some single logical nodes into two logical entities. Overall functionality of two separated entities is kind of equal to functionality of just one predecessor node. The difference is, first entity handles only control plane traffic and gives short commands to the second entity, while second node's main responsibility is to handle huge user plane load. Let's talk about some examples of such functionality separation in packet core network. SGSN node handling mobility management functionality in 2G and 3G networks take care of both control plane and user plane traffic. Latest specs releases allow to configure user plane traffic to skip SGSN, but I never saw such exception implemented in practice. 4G mobile networks came with MME node, which functionality is similar to SGSN's one. And MME was initially designed not to route user plane traffic through itself at all. Among MME's functionality is to control organizing user plane traffic directly between eNode B and S gateway and further to P gateway. More than 6 years MME working as control plane node only on mobile networks across the world. And then specs releases came with an exception of sending via MME small bursts of user plane data from IoT, Internet of Things devices. But I consider it as just one single specific use case as an exception, and it's about very small portions of data, because IoT devices are intended to save batteries and not making regular power-consuming procedures like other UEs make. IoT devices awake from time to time, send small amount of data from sensor or devices, and then turn back to long nap again. I would say MME in general was the first practical example of functions separation in packet core network and being control plane node only. Another example is about S gateway and P gateway nodes in 4G networks, which both initially handle control and as well user plane traffic. But on the way to 5G, they split their functionality. S gateway C and S gateway U came separated from single S gateway node. P gateway C and P gateway U came separated from single P gateway node. C and U suffixes are about type of traffic which separated node handles. C for control plane, U for user plane. It is important to understand that it's not just logical separation into two nodes. It's about balancing and redistributing traffic. In live network, one S gateway C node can control several S gateway U nodes. That's important since S gateway U and P gateway U nodes are highly loaded with user traffic. The closer node's processor, CPU, or interface or any other types of load to 100% of respectful capacity, the more chances for services to be rejected by overloaded node. That's why operator plans an expansion by adding extra node to rebalance traffic. With control plane and user plane functionality separation, it becomes easier to do. Operator no longer needs to install monolithic single node containing both control and user plane functionalities during network expansion. Just one node type which is close to be overloaded, likely user plane node. 5G networks came with just one user plane logical node in its core network, UPF. All the rest nodes in CN are handling control plane traffic only. So functional separation is naturally implemented in 5G core networks. The benefit of such control and user plane separation is obvious. It allows independent node scalability. Imagine an logical example. If you own a company with trucks fleet and you discover that amount of cargo to transport increases, maybe you can replace existing vehicles for larger ones or add more trucks. You can still control logistics, maybe even with the same amount of personnel, your control plane. But potential overall capacity can be increased by your renewed truck fleet, your user plane scaled independently. Functional separation in action. Another next improvement happened with mobile networks. It was nodes virtualization. It came to the picture after 4G networks were deployed and were working for more than 5 years worldwide. And it was few years before 5G to come. What virtualization we're talking about in this context? A little bit history with an analogical example. A long time back we had a huge helper handheld calculators. They made a lot of math work for us. I have few friends who worked till almost recent days for Texas Instruments in Department of Testing such devices. It was a special device provided by company, with own hardware and software. But most likely you're familiar with a lighter version of calculators. Instead of specialized hardware, you can find calculator in your computer or even small mobile phone. What happened? It became just a piece of software running on a kind of standard common hardware. What's important? Same functionality can be achieved even with a lighter version of software calculator compared to its grandfather's handheld one. Very similar situation happened inside mobile networks. Historically, there were just few vendors, with their mergers though, which produced proprietary equipment combined with proprietary software to implement mobile network nodes, which we have been talking about, RAN nodes and CN nodes. They are Ericsson, Nokia, Siemens, Alcatel-Lucent, Cisco, Samsung, and few more. So it was not much competition. But operators purchasing some equipment decided to increase competition and decrease costs, and requested mobile networks vendors to implement nodes as just software running on a standard off-the-shelf commercially immediately available servers, hardware, similarly to calculator software running on smartphones. Mobile network software-only nodes can run on servers which should have enough calculating and networking power to handle appropriate amount of generated traffic. By the way, good prerequisite for that, unification of IP-based transport. Such software nodes are named virtual nodes because they can potentially run on any equipment with standard operating systems, OS. They don't need proprietary hardware or OS to live on. That shift allowed to bring new just software development players on the market, like Affirmed Networks, Mavenir, and some others, to write code for mobile network virtual functions only and not focused on own equipment. There might be even further industry transformation, when extra layers could appear in mobile telecom domain. Companies like Amazon, Microsoft, Google, and others could bring cloud services, lots of their own virtualized servers, so vendors may not even own and being responsible for up and running equipment, but just being focused on mobile network nodes functionality, billing, and end customers. Servers with pre-installed OS may require more parallel computing power, and even hardware can be transformed as well by new players like NVIDIA, which can utilize graphic processors' parallel compute power for mobile networks needs. Does virtualization bring any other advantage to operators besides more competitive market from technical point of view? Potentially it may. Let's think about mobile networks load dynamically changing throughout the day. During business hours, a lot of people may work in the city centers, and in the evenings they drive home to outskirts. Therefore, mobile networks rush hours are geographically moving. During rush hours, traffic can reach maximum network nodes bottleneck capacity, with risks of having network overload and service rejects. With virtual deployment, if operator has hardware off the shelf, distributed geographically, it may quickly kind of move its virtual nodes closer to the rush hour areas whenever is needed, preventing network overload. Two assumptions underneath such benefit. Virtual node can be pre-configured and start working nearly immediately once switched on, assuming virtual environment and hardware underneath it are available. And similarly, can stop working quickly whenever is needed, like your software calculator can stop on your mobile device. And second assumption, mobile operators have very expensive licenses on limited number of software nodes, each node with its licensed max limited capacity. For example, maximum subscribers number. In other words, operator cannot add extra nodes in a city center without purchasing new licenses. But if operator can quickly switch off on virtual nodes, it allows to quickly disable some nodes taking care of city center geographical area and immediately enable same amount of nodes taking care of suburbs without going beyond number of licensed nodes working at a time. Isn't it elegant, convenient, and allows dynamically regulate traffic with extra overload preventive care? That's another potential benefit of virtualizing mobile networks. Next improvement in mobile networks is network slicing. What is it? Let's fly high and look to all mobile networks customers from high altitude perspective. They are not equal. Some of them require different quality of service, different quality of experience. If you may not care about intermittent delays when receiving email or message on your mobile phone, there are some customers who critically rely on extremely fast throughput, ultra-high availability, and ultra-low continuous network latency, which is time for data travel between source and destination. Just imagine possible use cases when mobile network may be involved. Vehicle-to-vehicle, V2V communication, when vehicles can communicate with other vehicles around on a road and potentially prevent collisions at a high speed. Vehicle-to-infrastructure, V2I, when vehicles can receive over-the-air information about traffic lights or speed signs to help avoiding any accidents. Medical emergency, when patient's body indicators like pulse, blood pressure, breathing characteristics need to be constantly sent from emergency vehicle to emergency room on the way to the hospital. Or even futuristic case, like remote surgery, when virtual reality techniques could allow surgeon to work remotely, constantly receiving video from surgical room and send signals from sensors reading his arm's movement to robotic arms in a surgical room. These are all services which require different mission-critical level of services to be provided for mobile devices involved in communication. We know how many nodes are inside mobile network. Remember RAN and CN parts discussed earlier. And they're geographically distributed, sometimes on a very large distances. There is a risk of having delays and not achieving end-to-end constant low latency with such unification, meaning using the same nodes for all subscribers. Network slicing comes into picture here and introduces network subparts, network slices, with own nodes, delivering certain quality of service to users utilizing this network slice. Previously discussed control and user plane separation, as well as mobile network virtualization improvements, are huge helpers to deliver slicing functionality. To achieve low latency between sender and receiver, you can guess we need to have shorter overall distance between them. For ultra-low latency experience, we need to squeeze all network nodes involved in end-to-end communication to be geographically very compact and closer to the customers. City infrastructure for V2I, V2V, hospitals for medical emergency or remote surgeries, etc. That could be achieved by enabling virtual CN nodes very close to radio network components to be used by customers. So this particular network slice with own nodes chain provides certain reliable ultra-low latency experience, while another network slice of the same operator with different, more distant network nodes for other customers to deliver regular services without such critical requirements. That's about network slicing with parts of mobile networks, slices, configured and tuned for specific use cases with different customized requirements. And the last improvement I want to mention. It's about unification and simplifying high-level language, protocol, and data structures it uses on large amount of interfaces in 5G network. Previously, we discussed unification of transport protocols to use IP protocol, which is responsible for data delivery between nodes. But nodes require some semantic meaningful information to be carried by transport layer protocols. High-level protocols with important content for nodes communicating with each other in focus for now. Similarly, if previously we talked about unified transport network using IP protocol, compared to trucks driving on unified roads, then now we talk about content, what those trucks are delivering. They are to carry standard packages of the same dimensions with documentation inside on the same language, for example English. Historically, there were much more high-level protocols in mobile networks, but in 5G there are just very few left. Lots of interfaces between 5G nodes to use HTTP2-based protocol leads to simplicity, and simplicity is a key for easier nodes integration, maintenance, and network issues troubleshooting. That's all that I wanted to talk about regarding main historical improvements in mobile networks. We started with unification of transport protocols with common player IP protocol. Then we mentioned that even voice calls started using IP-based packet data transfer underneath. After that, we moved to semi or even fully automatic mobile network parts configuration, where we discussed dynamic IP routing with automatic announcements possibilities of newly added network subnetworks, then automatic neighbor relations mechanisms for discovering adjacent radio network nodes, and also mentioned quick one request with one response message allowing to establish connection between two mobile network nodes. After that, we discussed control and user plane nodes separation with benefit, independent node scalability when required. Next subtopic was mobile network nodes virtualization, which brought new, just software development companies into this industry, making competition to vendors with old proprietary all-in-one hardware and software solutions. That allows in general to use standard hardware off the shelf, bringing new players to the mobile network market, and potentially allows to dynamically redistribute traffic. Then we discussed network slicing, where mobile network parts, slices, are configured for certain expected customer service levels. And finally, we mentioned unification of high-level protocols involved, bringing less and less protocols in newer mobile network generations. Let's wrap up and remember which main topics we have discussed about mobile networks throughout all 4 video parts. We started from history of wireless. We mentioned avalanche-like series of technological inventions. Remember semaphore telegraph, electrical telegraph, wired telephone, manual and automatic telephone call switching, radio, bidirectional radio services. Second topic was about mobile networks utilizing previous inventions and taking care of at least 3 components to be named as mobile network: telephone service over the air, electronic automatic phone call switching, and procedures for seamless communication when mobile users geographically moves even on a long distance. Third topic was about evolution of mobile networks throughout 5 generations. 1G networks were about voice and voice supplementary services mainly. 2G networks introduced SMS and packet data transmission. 3G networks increased data throughput compared to 2G networks' capabilities. 4G networks are fully packet data networks with even more increased data throughput compared to 3G networks' speeds. 5G networks brought even higher data throughput, higher connection density, for example for massive machine-type communication, ultra-low latency. We also discussed benefits of packet data type transmission with starting exploring RAN and CN parts involved in such transmission with tree-like hierarchy, where RAN part was historically a bottleneck. Fourth topic was about evolution of our bottleneck, radio resources, from mobile networks generation to generation. We discussed what mainly impacts overall data throughput and radio channel bandwidth was the first one on the plate. How channels can be shared during packet data transmission, and how resources can be allocated per user was second subtopic. We started with non-effective FDMA resource allocation, with one channel solely allocated for one user. Then we discussed TDMA technology, came within second generation networks on the top of FDMA, Later WCDMA in 3G and OFDMA in 4G and 5G technology appeared with their improvements and throughput increase. Third item allowed to increase throughput even more was special modulation of radio signal, which we compared to kind of archiver, amount of data squeezer over the air. Remember QPSK, 16 QAM, 256 QAM, 1024 QAM modulation examples. Fourth subtopic impacting on data throughput over the air was about few things. Carrier aggregation, simultaneous use of several radio channels up to 5 in LTE per one user. MIMO technology, using multiple transmission and receiving antennas even to send data on the same frequency at a time. Up to 4 antennas at transmitter and up to 4 antennas at receiver in LTE. Massive MIMO with antennas arrays, for example 64 to 64 in 5G. Beamforming and beam steering technology. Fifth subtopic was about high-frequency millimeter wave resources in 5G networks, which naturally allow to have radio channels with very wide bandwidth directly affecting increased data throughput. Next, fifth topic was about what is inside mobile network. We mentioned three main subcomponents: user equipment, radio access network, and core network subsystems. We were not focused on separate billing, charging subsystems, as they are not involved in services delivery. We went deeply within each of three main subcomponents and discovered how many nodes are inside mobile core networks. There are databases storing information about subscribers to be used later for identification, check-in supplementary services subscription, and authentication. There are nodes which take care of mobility management function, tracking subscribers' state and location. Other nodes about session management functions and routing user traffic throughout mobile network, which we compared with constructing pipes and oil transmission via those pipes. And few other nodes were mentioned as well. And the very recent sixth topic was about interesting historical improvements. Paradigm shifts happened with mobile networks. Unification of IP protocol-based transport and high-level protocols between nodes. Voice over IP, semi or fully automatic network parts configuration, control and user plane nodes separation, nodes virtualization, and mobile network slicing. I hope you enjoyed these videos about mobile networks and discovered something interesting for you, something likely new, and made parallels with other work and life aspects. Hope you not only enjoyed but also understood what mobile network is, what it can do, and what parts it consists of. Topic for the next video to discuss is why do we need to learn about mobile networks, how it might be useful and interesting for you. Hope to see you there.